Today we'll be proving ourselves some quadrilaterals to be parallelograms, and this will be a continuing theme throughout the rest of this chapter, where we prove quadrilaterals to be a more specific type of quadrilateral, like a square, or maybe a rectangle, or a rhombus, or a trapezoid, or a kite. All right, so we will continue to prove different types of quadrilaterals. Today we will focus on parallelograms. So here's all of our ways of proving that a quadrilateral would be a parallelogram. These are all the reverse, the converse of the ones we wrote down in the last video. This is the one that we added in, I believe, at the very end, where it's not really a property of a parallelogram, but it is a way to prove the parallelogram, prove that it is a parallelogram. And it's one pair of opposite sides of a quadrilateral are both parallel and congruent. And I want to reiterate that it needs to be, if these are the opposite sides we're saying are congruent, these are the ones that also have to be parallel. It can't be like this kind of a situation where these are parallel and these are congruent. That does not work. No way. Okay? No bueno. Only the top one right up here would work. All right, we are not going to actually do the proof on this one. I would rather work on a couple other problems and save a little time. But I want to reiterate that all 5 of those can be proven using a 2-column proof. They can be proven to be true, okay? And that's the only way we can use a theorem, is if they can be proven to be true. And this one can be. We're not going to go through it. We'll do a couple other problems instead. YOLO. So this is from page 251 in your textbook. For each one of these, you want to state the property or definition, if there is one, that proves the quad to be a parallelogram. Okay? Now, one or more of these may not be, but we want to see which ones are. Okay? By the way, those little circles that are on those are congruent marks. So those are congruent segments if you see the little circles on them. Take a second, pause the video, and then I'm going to pop the answers up here in just a sec. Alright, here's what we got. The first one, top left. Those diagonals are bisecting each other. Therefore, we have a parallelogram. B, right below that. One pair of opposite sides is both congruent and parallel. That's what the arrow and the double tick marks mean. C, opposite sides there are congruent. D, nope. One pair of opposite sides is congruent. The other pair are parallel. That is not necessarily a parallelogram. It could be an isosceles trapezoid, which we haven't gotten into yet. But I could have those two parallel and these two congruent. I have the same information I'm given there, but it's a totally different quadrilateral. So we can't say fauche that it would be a parallelogram. Okay? And the last one, I said opposite sides are parallel, then you have a parallelogram. I only see one pair of opposite sides parallel. Ooh, what about these two? Take a looky here. You got a transversal, these two opposite sides. Those are alternate interior angles that are congruent, therefore I have parallel sides. Sorry, my lines are a bit off, but I hope that you get the picture there. Cool. So I would be able to show that UA and QD are parallel, and then I'd have an pair of opposite sides parallel. Awesome. All right, so I've got these 4 coordinates here, and I want to prove that PQRS is a parallelogram. It's the only quadrilateral we specifically know about right now, so that's all we're going to show, is that it is a parallelogram. There is a little strategy for these types of problems that we'll continue to reiterate here throughout this chapter, and it's that we want to focus on our slopes at first. A lot of times we want to go write the distance formula and be like, oh, I'll just show the opposite sides are congruent. That can be kind of a pain in the butt, doing distance formula 4 times, okay? So in this case, I'm gonna check my slopes here. Now my slope of PQ is 0, and SR is also 0. It's a horizontal line, so my slopes are 0. So I know that those are parallel. Well, how about my slope of PS? I could either count it out, which would be, my rise would be, looks like 10, and my run is 3. So up 10 over 3, and it is a negative slope. 10 over 3, negative. All right. Or I could use my slope formula for that. And then, again, I'm going up 10 and to the left 3, so this is also a negative 10 over 3. So what do I see here? I have 0 slopes for my horizontals, those 2 lines there, and I have a negative 10 over 3 slope. Well, what does that tell me? If they're the same slope, they are parallel. So I have these 2 sides are parallel, these 2 sides are parallel. If the opposite sides are parallel, I have a parallelogram. All right. Now in the future, when we start dealing with rectangles which have right angles, I would be looking for maybe opposite reciprocal slopes for my consecutive sides. So I'd want, like 0 and undefined, or I'd want 3/10 and -10/3, right? Those are opposite reciprocals. But we'll get there when we get there. For now, I've got my opposite sides parallel. I have shown that this is a parallelogram. I am done. And maybe I'd write something like opposite sides parallel, then parallelogram, saying how I figured it out, right? We looked at our slopes, we Gucci. All right, so I've got triangle CAR is isosceles with base CR. I've got angle C is congruent to angle K, and AC is congruent to BK. Let's jot some of this down in here. So AC and BK are congruent. I've got angle C and angle K. I also have that CAR is isosceles with base CR, which would mean that CA and RA are congruent. So what I'm seeing here now, because I only did one tick mark because that matches CA, I'm seeing that I could do maybe AR is congruent to BK, right? Either by substitution or transitive property would link those together. So I've got that in the back of my mind. Okay. If it's an isosceles triangle and I've got those congruent legs, wouldn't I also know that C and R are congruent? Yeah. And it looks like to me, once again, similar idea. Let me fix that arc there. Okay, that's a little better. Say ARC, that angle right there, which is congruent to C, would also then be congruent to K by transitive or substitution. Ooh. Ooh. Hold up. Hold up. Take a look at these two lines and that transversal. If you look at the angle K and the angle ARC, those two angles are corresponding angles, right? And if they are congruent, I get parallel lines. That would mean that AR is parallel to BK. One pair of opposite sides is both parallel and congruent. What do I get? A parallelogram. That is one of the most frequent ones you will use to prove that you have parallelograms. Okay? So again, when I approach this problem, if I want to prove that bark is a parallelogram, I'm looking maybe for opposite sides congruent, opposite sides parallel, opposite angles congruent, or one pair of opposite sides both congruent and parallel. And there's a couple others, but we'll get there when we get there again if we come up to that situation. This is probably the most frequent situation though. All right, so let's write it up. We've got ourselves a parallelogram. So I got my given. And there was a lot that we did there. So let's see here. How about AC is congruent to AR? And that was by def iso triangle, right? And then I also had that angle C is congruent to angle ARC. If sides, then angles. And the reason why I'm doing those two back to back is so that I can save myself a little step here, and I can say that AR is congruent to BK, and I also have angle AR, oops, sorry, not right there. Oh my goodness, what am I doing? Angle ARC is congruent to angle K, and that's both by transitive property. Now, some may or may not want you to combine those into one step because one of them's talking about segments, the other's talking about angles. But really, neither one of those statements depends on the other one happening, right? AR and BK can be congruent from transitive property, and ARC could be congruent to K by transitive property, and it doesn't bother the other one. So that's why I'm putting them together, okay? If you want to separate them, that's cool. I'm going to put them together, though, because I'm crazy like that. Okay, so now that I've got those angles congruent, that allows me to prove that AR is parallel to BK. And that is because corresponding angles congruent, then parallel lines. Yeah. And I've got Let's see here. One more steppy step. I've got parallel lines, parallel opposite sides. I've got congruent opposite sides. Therefore, I have parallelogram bark, or bark is a parallelogram. My reason? One pair, opposite sides, congruent and parallel, then parallelogram. Heck yeah. That was a super cool, awesome, dope proof. America. Alrighty, last one from the day here, and I see a congruent sign floated away, so I'll just rewrite that right there. Cool. Ooh, I wonder if you can hear the tornado sirens that are going off right now. It is the first Tuesday of the month at 10 o'clock, so they're going off. Alrighty, so I've got AC DF is a parallelogram, so I get all the information of a parallelogram. Opposite sides congruent, opposite sides parallel, opposite angles congruent, all sorts of good stuff, right? I've also got that AFB. AFB is congruent to ECD, those two angles. And I want to prove that inside guy to be a parallelogram. Okay? Sounds lovely. Now, there's actually several ways of going about this one, so I'm gonna do one of the ways, at least one that makes sense to me. If I have a parallelogram, I know that my opposite sides are congruent, right? So are these, okay? I also know that my opposite angles are congruent in a parallelogram, right? Those two, and then also AFD and ACD. I'm not going to use those ones, so I'm not going to mess up the situation that I got going on. There is a way to use those. I'm going to do it a different way. All right, so what do I have right now? It looks like I've got those two triangles on the outside to be congruent, right? Angle side angle would prove those two triangles congruent. So if I've got those two angles, I'm going to move to green now for my post-triangle congruencies. I would have that AB and ED are congruent, yeah? I'd also have these sides congruent. Now, FB and EC are opposite sides of that smaller parallelogram. I wonder if I could get this guy and this guy to be congruent, right? Could I do that? Well, I've got AC congruent to FD, which are two big sides. If I subtracted AB and ED, I'd get FE and BC congruent, making that smaller one a parallelogram by opposite sides being congruent. I have a parallelogram. Sounds like it gonna work. Okay, so let's write it up. And again, this is one way of doing this one. I'm happy to go over some other ones in class with you guys if you'd like, or if you thought of a different way to do it, by all means, come check it with me. There are a lot of ways to do this particular proof. So I'm going to start with AF is congruent to DC, and I'm also going to state that FD is congruent to AC by, if it's a parallelogram, then opposite sides congruent. Then I've got my opposite angles. Angle A congruent to angle D. If it's a parallelogram, then opposite angles congruent. And I'm not even going to mention the other angles because I'm not going to use them. Step 4. I've got my triangles congruent, right? Triangle AFB. I got to make sure that I match them up now. Triangle AFB is going to match up with triangle D, not C. D, and then C, E. That's by angle, side, angle. And I prove those congruent so that I could get some sides congruent. FB is congruent to EC, and I was using AB is congruent to ED by CPCTC. Okay, so the FB and the EC, those are good to go, but I still need to talk about my subtraction property action. I can get FE congruent to BC, and that is by subtraction property, subbed prop. And now, now that I have those two congruent, I have a parallelogram, right? And that was parallelogram, I lost it there. So parallelogram FBCE, and my reason?
Could J.T. Adams, Ann Mercurio, Jack Landman, and Samantha Teresi report?
Boom, done. America, freedom, rock and roll. I gotta go to class, dogs.